Welcome, everyone. So happy Pi Day, everyone. When I was an undergraduate here at the University of Sydney, I had a flatmate who was studying law. And he came into my room one day and said, "Geordie, let's make a deal." And I was a little bit suspicious because he was a lawyer and I wasn't. And he said, "If you learn the first 1,000 digits of pi, I'll learn the Australian Constitution." And we went for about 10 days and I learned about 10 digits of pi and he learned about 10 words of the Australian Constitution. And we got nowhere. So it's really great to have Oded here today. He is an associate professor at the University of Sydney. He was born, I believe, in Israel, grew up in Washington, outside of Seattle.
That's right.
Did his PhD in California, did postdocs in Toronto and Sydney, and we're very delighted that he decided to stay on in Sydney. Also, he had maybe a year or two back in Israel.
That's true.
And he's talking about the work of Galois, who is a very dear figure to a lot of us in the maths department. I should mention that this is hosted by the Sydney Mathematical Research Institute, and it's very unique in that we have, I think, the youngest members that have ever attended a public lecture. We have Noam and Danush, who are Oded's kids, and we have some other kids here, which is really great to see. So welcome. So without further ado, I'd like to welcome Oded, talking about Duels and Duality. Thank you very much.
Thank you. Thank you, everybody. Thank you so much for coming. I'm super excited you're all here. And I'm really excited to give this talk. Before I get started, I thought I need to get a bit of an idea of who's here. Kind of helps me gauge how to give the talk. So I was wondering, can you please raise your hand if you're a high school student right now? Awesome. Thank you. Can you please raise your hand if it's been maybe, I don't know, about 20 years since you've been in a math class, and in those intervening years, you haven't used the word polynomial in the complete sentence? All right, very good, very good. And what about uni students? Are there uni students here? Fantastic, all right, great. This is very helpful for me. So the reason I'm so excited to give this talk is because I get to tell you what I think is the greatest story in the history of mathematics, and I'm not exaggerating. And it's amazing both from like a human perspective and from a mathematical perspective. And my goal is really to give you an understanding of both sides of that story, and hopefully in the end try to relate it a bit to our lives. All right, so let's get started. This is the setting, early 19th century France. It's a very tumultuous period of history. There's the French Revolution. People are trying to overthrow kings. There's riots in the streets of Paris. And in this particular period, in 1832, there's a group called the Republicans. These are the people that are trying to overthrow the king, and they're provoking these riots in the streets, and they turn a bit violent. And one person who was at this riot was Victor Hugo. And you may be familiar with some of this story because the climactic final scenes of Les Miserables are exactly about this so-called June Rebellion. But actually, I'm not here to talk about Victor Hugo. I'm here to talk about somebody else who wasn't actually at this June Rebellion, because he died just less than a week before it started. And the main character of our story is this guy, Évariste Galois. This is a portrait of him that was made when he was about 15 years old. And he was just this brilliant and often misunderstood math student. He died at the young age of 20. And he was a very, very passionate political activist, kind of taking after his father. And this got him in trouble many times. He was expelled from his university, and he had many stints in jail. And his final stint in jail was right before this June Rebellion, that week leading up to it. And the day before he was going to be released from prison, he spent the whole night furiously writing a letter to his friend. Because he knew, well, actually, before I say that, let me show you some copies of this letter. These are some surviving copies of this letter that he wrote. And it's a bit messy. And that is probably understandable because he was a bit stressed. And that's because he knew that the next day he was going to be released from prison and he was scheduled to fight a duel. And he knew that chances were not slim, and indeed, he was released from prison. He fought the duel, took a gunshot to the abdomen, and died a few hours later. And so he spent these final night of his life writing this long letter. I should say that historians are not exactly sure what precipitated this duel. Most think it was about a woman. And in fact, if you look at the scribbles on the right-hand page on the lower left side, there's the words une femme, and then it's kind of crossed out. But it turns out, so the question is, what was he writing about in this letter? It turns out Galois wasn't just a political revolutionary, he was also a mathematical revolutionary. And in this letter that he wrote to his friend, he described a solution to a problem that centuries of mathematicians have been trying to solve. And he claimed, and mathematicians, like some of the greatest mathematicians in history, names you might recognize like Gauss, Lagrange, people were very interested in this problem. And he claimed he finally found a solution to it. And this was amazing. But more than that, his solution itself was so revolutionary that it started a whole new area of mathematics, an area that today we call abstract algebra. And this area of mathematics is hugely influential within mathematics, and also it actually affects our day-to-day lives as well. And that's something I want to get to as well. So what I want to try to explain to you right now is actually what the mathematics that he wrote about. What was this problem that he solved? And how did he do it? And what was so revolutionary about it? So to begin, let's look at this equation. So this is our first equation. So those of you who have not looked at math equations for a long time, this is where it gets real. So, okay, so let's think about what's happening here. There's a variable x, and we have this equation that says ax squared plus bx plus c is equal to 0. Okay, so a, b, and c, these are called coefficients. There are think of them as some like fixed integers. And what does it mean to try to solve this equation? It means you're trying to find values of x where this equation becomes true, where ax squared plus bx plus c is equal to 0. And this is called a quadratic equation because the degree of x, the highest degree of x that we see there is 2. We see an x to the power 2. And so we call this a quadratic equation. And there's a very famous formula that gives us a solution. Does anybody know the name of this formula? The quadratic formula. And it's this right here. And it might, if you haven't seen this kind of thing in a long time, or if you've never seen it before, that's totally okay. It looks a tiny bit complicated when you first look at it. But let's just try to understand what's happening. We're trying to find solutions of this equation. We're trying to find values of x where this thing is equal to 0. And this formula gives us what those values are. It tells us that x is, okay, minus b plus minus square root of b squared minus 4ac on 2a. The exact technical details are not important. But let's look at let's look at a small example. For example, if I look at this case, x squared minus x plus 2, so then a is equal to 1, b is equal to minus 1, and c is equal to 2 in this particular case. And if you take those values of a, b, and c and plug them into that equation, you get this formula for the roots. That means that for these two values of x, minus 1 plus root of minus 7 on 2, and minus 1 minus root of minus 7 on 2, if you take either of these two values and plug it into this equation, it's true. You get x squared minus x plus 2 is equal to 0. Okay, so like I said, I'm not worried that we remember like the technical details or have to remember this formula, but there's two things that I do want us to focus on in this slide. One is that the answer, this formula, it gives us, it's in terms of the coefficients, these a, b's, and c's that pop up into the equation. And then we have to use some sort of algebraic operations to produce the roots of this equation, right? So we're doing like addition, subtraction, multiplication, division, and very crucially, there's a square root in there. And so we're taking these coefficients that we started with, a, b, and c, and we're combining them in a special way using these kind of algebraic operations, and that produces the answer. That's one really important thing about this formula. And the other important thing about this formula, like for instance, if you look at our example, there's a square root of minus 7 that pops up. Does anybody feel a bit weird about square root of minus 7? If you played around with numbers, usually when we take a square of a number, the result is non-negative. If I take minus 3 and square it, I get 9, something non-negative. But here we're saying a square root of minus 7, something whose square is minus 7. And we see that, so this turns out to not be a real number. It's an example of what's called a complex or imaginary number. Okay, and these are fine, but the point is that we started with this very innocent looking equation, x squared minus x plus 2. We try to look for a solution. And immediately, we have to leave the world of rational numbers or real numbers and go to imaginary numbers. We have to enlarge our number systems to find the solution for this equation. And that's the second really important thing about this formula. Okay? Okay, so we have this nice quadratic formula. This was actually known since antiquity. The Babylonians knew the quadratic formula, although they wouldn't have written it in this kind of notation. But this has been known for thousands and thousands of years. And a very natural question that might pop up is, okay, like why focus on this degree 2 thing? Why not look at the same question, but for cubics? That is, polynomials or equations like this where the highest power of x is 3. That's a natural. You might ask the same question. So you start with something like ax cubed plus bx squared plus cx plus d equals 0. So you have the highest power of x is 3. And you ask the same question. Can we find a formula for the zeros to solve that equation? And it turns out that's a much, much harder problem. And although, as I said, we've known the quadratic formula for thousands and thousands of years, it took mathematicians until the Renaissance, Italy in the 16th century, to find what's called the cubic formula. And this is also a very interesting story. You had these dueling mathematicians. So on the left-hand side, there's Tartaglia. On the right-hand side, there's Cardano. They both claim to know the cubic formula. It means they know how to take equations like x cubed plus 2x plus 1 and tell you what the zeros of that equation are, what the roots of that equation are, but they wouldn't tell each other. They kept it a secret. And they started these kind of like intellectual battles, these duels where they'd say, you know, Cardano would say to Tartaglia, here's a cubic equation. I know the roots. Do you know them? And Tartaglia would come back and say, here are the roots. Here's another one. Can you do it? And this was like a hotly debated topic. It was very public. People were following this. It's kind of amazing. And it turns out they both knew the answer. They both knew the cubic formula. And it looks something like this. It's much, much more complicated the first time you look at it. So you have you have a cubic formula, a cubic equation on the left-hand side. Remember, that means the highest power of x is 3. And we're trying to ask for zeros for this equation. And you get some formula that looks way more complicated than the quadratic formula, but it's somehow still very similar. The answer is still written in terms of coefficients. And the answer is still, you know, you still create the roots using some sort of algebraic operations. Again, addition, subtraction, multiplication, division, square root. And here, crucially, we see something new. We see a cube root, right? But it's still the same general idea. And then, okay, so we can do quadratics. We can do cubics, degree 3. What about degree 4? Just, you know, keep on it. It's very natural. Next question. And 10 years later, after these were this cubic formula was publicized, it turns out very similar methods were able to solve the degree 4. And I won't show you the formula. It's not important for us. And so then, all right, let's keep the party going. How about degree 5? And then things hit a wall. And it turns out none of the methods that worked for degree 3 or degree 4 worked it for degree 5. And nobody really understood why. So for the first couple hundred years, people were, you know, really energetically trying to solve the quintic, the degree 5. And after a couple hundred years of efforts, and I'm saying like this was like one of the most prominent problems in mathematics at the time, people were really, really trying to study it. And after a couple hundred years of efforts by work of mostly Lagrange, it came to become a little more pessimistic and realize that something was different about degree 5, but they didn't really understand why until 1824. This mathematician, Niels Henrik Abel, a Norwegian mathematician, proved this following bombshell theorem. It says the quintic has no general solution. So what does that mean? Let's try to understand what this means. Quintic refers to degree 5. So just like before we saw where the quadratics where the highest power of x was 2, and we saw cubics where the highest power of x was 3, quintic refers to a similar equation where the highest power of x is 5. And when we say it has no general solution, what that means is that there's no sort of analog of the quadratic formula for a degree 5 polynomial. So you can't, but there just does not exist a formula in terms of the coefficients of the polynomial and any algebraic operations you can think of. It could be square root, cube root, a millionth root, doesn't matter. You can't find a formula for, in general, that would work for every single degree 5 equation. And just as an aside, actually 2 asides. One is that Abel was also an amazing mathematician, an amazing figure in history. He also died at a young age, at 26. One could devote a whole other lecture just to the stuff that he did. You might recognize his name because there's the so-called Abel Prize, which is sometimes considered like the Nobel Prize of Mathematics that's named in his honor. Another thing I want to mention is that this is often referred to as the Abel-Ruffini theorem, if you try to look this up, because his work, although he was the one who finally pinned down this proof that the quintic has no general solution, it builds using some serious earlier work of a guy named Ruffini. Okay, so this, in some sense, seems to end the story. We know how to do degree 2, 3, 4, and Abel tells us we can't do degree 5. So let's go on and do other things. Why still talk about this? Well, it turns out that although this was a major advance, it still left some huge gaps in our understanding of what was going on. For one thing, Abel, although his proof his methods, you couldn't point to any single example of a degree 5 equation that has no solution. It's very easy to write down examples of degree 5 polynomials where we can write down a solution. Abel tells us we can't do it in general, but he can't point to a single example of where that's not possible. And more to the point, I think he doesn't tell us why. Something is different about degree 5. And this is where Galois really enters the picture. So if I had to summarize what Galois did in one sentence, I'd say that he tells us to study solvability in terms of symmetry. So what does that mean? Well, solvability is what we've been talking about. It's trying to find solutions to these polynomial equations, trying to find solutions to these things like the quadratic formula or the cubic formula. And so that's the question we've been talking about so far. But what is symmetry? Well, symmetry is what we all think symmetry is. It's the same thing that we talk about when we use it in day-to-day language. So, for example, here's a picture of a plant. This image exhibits symmetry because if I take it and rotate it by 1/5 of a full turn, it kind of goes back to itself. So I'd say this image here has some sort of bifold symmetry. And on the face of it, solvability and symmetry seem like two completely different things that don't really have anything to do with each other. So I want to explain why they're actually intimately connected. But before I do that, I want to try to delve into the idea of symmetry in a bit more detail. And I think a good example to take is to think about a square and ask the question, what are the symmetries of a square? So for example, here I have a picture of a square. I've labeled the corners to kind of help us keep track of what's going on. And if I take the square and rotate it by 90 degrees, I would say that's an example of a symmetry of a square. Why? Because the result, I mean, you're taking a square and rotating it, but the end result is the same as what you started with. And we can see I've labeled the corners to help us keep track of what the operation is. When you rotate the square by 90 degrees, the corner labeled 1 goes to where 2 used to be, 2 goes to where 3 used to be, 3 goes to where 4 used to be, and 4 goes back to where 1 used to be. Okay? Can anybody think of other symmetries of a square? I heard somebody say reflection. That's true. That's coming up. But actually, I want to first think more about other rotations. So rotating by 90 degrees is one symmetry. Another thing we can do is rotate by 180 degrees. That's again a symmetry. And here again, I've labeled the corners to help us keep track of what happens. So 1 goes to where 3 used to be, 2 goes to where 4 used to be, and so on. Okay, and you can keep on going. You can rotate by 270 degrees. That's another symmetry. And finally, you can do a full turn, rotate by 360 degrees. This is again a symmetry, but this is a very special one because it's kind of lazy. Although we did a full turn and every point ended up where it started. Okay, and that's also an important one, but it's kind of different from others. And there are other symmetries of a square. As I heard people say before, there's also reflections. So for example, if I take the square and reflect along a vertical line, this is an honestly new symmetry because now 2 and 4 are fixed, but 1 and 3 interchange places. Yeah, and I can keep on doing this. There's other types of reflections. For instance, reflection on a horizontal line. Now 1 and 3 are fixed and 2 and 4 trade places. And similarly, you can do reflections on the 2 different diagonal lines. Okay, so these I would say are all the symmetries of a square. And I want to think of them all together. And so let me list all 8 symmetries that we just introduced. And hopefully this is some suggestive notation. I have the 4 rotations, like rot 90 stands for rotation by 90 degrees. Rot 180, also there's rotation by 360 degrees. Remember, that one is special, so I want to give it a special name. I'm going to call it id for identity. Okay, so we have the 4 rotations on top. And then the 4 reflections on bottom. And so we have reflection in the horizontal line, vertical line, and the 2 diagonal lines. Okay, so this is good. We have all the symmetries of a square. There are 8 of them. Now, the kind of abstract jump that we need to make next is to not think of them individually as a list of 8 different things, but really think of them as one collection. So we say the symmetries of a square collected together, and we'll say we'll form a group that will give it its own special name, D8. So 8 stands, I use 8 because there's 8 elements, and D stands for dihedral, doesn't matter. Now, the word group here has like a technical mathematical definition. We won't need to get into it, but I do want to kind of pinpoint one essential structure that happens when you think about all of these symmetries together as one thing. Because I could do something like take one symmetry, apply it, take another symmetry, apply, and then take another symmetry and apply it. I can compose symmetries. And the result is again going to be a symmetry. Right? So for example, if I do like rotation by 90 degrees and then reflection on a vertical line, the result is reflection on one of the diagonal lines. Okay? So this is not just a list of 8 different things. There's also a way to multiply things together. And this multiplication, this relation between the different symmetries, this is the inherent algebraic structure that we can study. This somehow carries a ton of information. All right, so that's cool. We talked about symmetries of a square. But it's not clear what this has anything to do with the original question that I posed. And we're trying to find solutions to these equations. And so what I want to do now is I want to take an example where we can actually solve by hand and kind of look under the hood and see how Galois' ideas come up and how we can use symmetry to really understand what's happening. An example I want to take is this one. So degree 4, x to the 4th plus x squared plus 1 is equal to 0. And for this example, we don't need any highfalutin machinery to solve. We could actually just reduce it to the quadratic equation. Can anybody see the trick I would use? How would I try to, I want to find the roots of this, and I want to reduce this actually to a quadratic, even though it's a degree 4. Yeah, that's right. You guys got it. I want to do a sort of new variable. I want to do a change of variable. So what I'm going to do is I'm just going to invent a new variable. I'm going to call it y. I'm going to say, okay, y is equal to x squared. This is one of the things I used to love about math when I first started. You can just invent things. If it works, it's great. So we just invent a new variable, y. Say, okay, y is equal to x squared. If we take this original equation and write it in terms of y, we get y squared plus y plus 1 is equal to 0. It becomes a quadratic, right? And now we can apply the quadratic formula, and we get this result, that the zeros of y squared plus y plus 1 are given by minus 1 plus minus square root of minus 3 on 2. And now we just have to remember that y is equal to x squared. And so we solve for x, and we get 4 different roots for the original equation. I call them x1, x2, x3, and x4. And the exact details are totally unimportant. So I don't expect you to memorize this or to totally follow the arithmetic. The idea is just, okay, we can solve this by hand. We don't need to really think about this too deeply. One thing maybe we do want to notice is that these different roots of that original equation, they bear some relationships to each other. So for example, x1 and x3 are negatives of each other, and x2 and x4 are negatives of each other. So these roots of these equations, they satisfy some formulas, like x1 plus x3 is equal to 0, and x2 plus x4 is equal to 0. Okay? And here is where Galois asks the essential question. It's totally not obvious, which is, what symmetries do these relations satisfy? Okay, so what does that mean? Let's do an example. Maybe think about the operation of interchanging x1 and x3. Okay, so if I interchange x1 and x3, x1 plus x3 equals 0 becomes x3 plus x1 is equal to 0. That's still true. And x2 plus x4 is equal to 0. That doesn't even get touched. That's still true. So I would say that this operation of interchanging x1 and x3 and leaving 2 and 4 fixed, that's an example of a symmetry of these two relations. Okay? Contrast this with interchanging x1 and x2. If I interchange x1 and x2, then x1 plus x3 becomes x2 plus x3. That's no longer equal to 0. So I would say this is not a symmetry of these relations. Another example is the operation of taking x1 to x2, x2 to x3, x3 to x4, and x4 back to x1, like this kind of cyclic thing. And what happens to these equations if we do that? Well, x1 plus x3 equals 0 becomes x2 plus x4 is equal to 0. x2 plus x4 becomes x1 plus x3. They interchange roles, but overall, they're still both true. So this is another symmetry of these relations. And hopefully, these operations of interchanging x1 and x3 and this cyclic one remind you of the symmetries we saw earlier when we were looking at the square. Because interchanging 1 and 3 and leaving 2 and 4 fixed, that's exactly the reflection along a vertical line. And taking 1 to 2, 2 to 3, 3 to 4, and 4 back to 1, that's exactly rotation by 90 degrees. Okay? And in fact, if we ask the question of what are all the relations, sorry, all the symmetries that preserve these two relations, we get precisely the symmetries of the square that we studied earlier, this group DAs. And so that's, I think, something already pretty cool. We see these two things on the face of it don't seem that related. We see that we can somehow see the symmetries of the square in these two relations. But it's still unclear what this does for us. And indeed, this is the end of the story if we just allow ourselves rational numbers. So this funny symbol Q over here, this is the symbol that mathematicians use to denote the rational numbers or the fractions, like minus a third, 2 over 17, that kind of thing. And one thing that I wasn't super explicit about is that when I was writing down these relations between the roots of that polynomial, I was only allowing myself relations that can be expressed using rational numbers. But I don't have to do that. I can start adding numbers that are not necessarily rational, and I might get new relations. So for example, I can add square root of minus 3. This is one of those complex numbers that's not rational. And if I do that, I get this new relation that I couldn't express before when I just had rational numbers. The relation is x1 squared minus x2 squared equals square root of minus 3. Again, the details are not important. The important point to take away here is we started with this number system of rational numbers. We added something to it, and we got a new relation. That's the important point. And now we ask the same question, or Galois asked the same question as before. What are the symmetries of these relations now? Remember, so we had these two previous relations before. Now we found a third by enlarging our number system. And so the symmetries of these relations the question becomes, of those 8 ones that we already found, which ones also preserve this new one, right? So things are going to get smaller. And it turns out that exactly half of them, half of the original 8 that we found, preserve also this new relation. So the identity, which always is going to be in the mix, rotation by 180 degrees, reflection on a horizontal line, and reflection on a vertical line. And I call that's again an example of a group. I call it K for Klein. Okay? So the point again is that we enlarged our number system. That gives us somehow more freedom, so we got more relations, but then we ask for the symmetries of all the relations we found so far, and they get smaller. Okay? And we can keep on playing this game. This is by far the most technical side of the talk, and again, the technical details are not important. It's just the same game can continue to be played. We add a new number, let me call it omega. We get a new relation, happens to be x2 minus x4 is 2 omega. And then we ask the same question. What are the symmetries that preserve this relation and all the previous ones that we've seen so far? And it turns out there's only 2, the identity one and reflection on a vertical line. And I'll call that group Z2. Okay? And we could do this once more. Add one more number. Again, details are totally unimportant. It's just, okay, this one I'll call omega prime. You get a new relation, x1 minus x3 equals 2 omega prime. And the point now is that if we ask the same question, what are the symmetries that preserve all the relations we found so far? The group becomes as small as possible. It's just the identity. Okay? And so what we have actually done, and what this is fundamental to Galois' solution to this problem, is established a duality. Remember, when we started this picture, we found the group symmetries of the square. That was D8. And at that step, we were confined to using the number system, which is just rational numbers. And then we systematically enlarge our number system. We add new numbers like square root of minus 3 and this omega, one by one. And as we do that, the groups on the left get smaller and smaller. And it turns out these two sides of the picture are completely dual in the sense that the groups determine the number systems and the number systems determine the groups. You can go back and forth between them. And this is an amazingly deep result of Galois, and it's absolutely fundamental to his solution. And so now let me tell you about Galois' solution. Okay? Hopefully it blows your mind. So Remember, let's just remember where we are. We have this polynomial, like let's call it f of x, and we're wondering whether we can find solutions to it, whether we can find something like a quadratic formula that holds also for this polynomial. But now the polynomial can be any degree you want, 17, a million, doesn't matter. And the first thing Galois says is you can always do this process of associating a group of symmetries with a polynomial. Just like before we had this degree 4 guy, and we found the group D8, Galois tells us how to do this in complete generality. Start with a polynomial, you get a group of symmetries. And I'll call that group G. Okay, and before we saw a group that was relatively small, it had 8 elements, but these groups can be really wild. They can go crazy. A lot of different things show up. But the amazing thing is that Galois proves that solvability of this polynomial, the thing we're actually after, the thing that mathematicians have been trying to understand for hundreds of years, becomes a totally different question about this group. Totally different realm. So it turns out there's a property of a group called solvability. I'll get back to that in a second. But like the really important takeaway here is you take this problem they were interested in, transfer it to a completely different problem that's actually equivalent. And this is, so this is like absolutely amazing. And what is solvability? It's actually something we already saw. It's exactly this tower of groups that we saw in the example. Remember, we started with this group D8, then it got cut in half to this group K, and then it got cut in half to this group Z2, which then got cut in half to this group that was just the identity. So solvability means that that kind of thing can happen. You can find a tower of subgroups inside your group G, which behaves in a nice way. Okay? And if you can do that, if you can show that your group G satisfies this nice property, then you transfer this over to the world of polynomials and you deduce there is a formula for the roots of that polynomial. So it's absolutely amazing because it takes the one problem, makes it something completely different, where there's a whole new set of tools you can try to apply to it and ways of thinking about it. So for example, now you can use this work and say, here's an unsolvable polynomial. Doesn't look that crazy. 2x to the 5th minus 10x plus 5. If you take Galois' idea and run it on this example, you'll see that the group you get has 120 different elements. Before we saw a group that was size 8, this one has 120. It's much bigger. But the point is that you study the structure of that group, and it's not that hard to show that you can never find this kind of tower of nice groups sitting inside it. And so that means there is no way, how hard you try, no matter how hard you try, to find a formula for the zeros of this polynomial in terms of the coefficients in algebraic operations. It's just impossible. And you see here, this is the main difference between the work that was done before Galois, where we had no idea how to point even to a single example of a degree 5 polynomial that's not solvable. And I just want to stress here, before Galois did this, the notion of a group did not exist. This started a whole new area of mathematics. And it's absolutely amazing. And so you might be thinking, okay, you solved one problem. What else is this good for? It turns out a whole lot. So let me give you some examples. I want to start with some really, really ancient problems that the Greeks were really interested in. So the ancient Greeks were interested in this problem of taking, you have like a straight edge, which is like a ruler without any markings on it, and you can use it to draw straight lines. And you have a compass, which you can use to make circles. And the question that we're asking is, what can you do with these two operations? So for example, suppose I give you an angle, ABC. Can you use just a straight edge and a compass to bisect it, to split it exactly into two equal angles? Does anybody know how that would go? Any suggestions what I should do? Yes?
You can draw a circle centered around C and a circle around A, and then...
Maybe. Okay, sorry, I was thinking of a different way. But I like the way you're going with that. There's maybe a way to go where you start with a circle centered at B. Okay? And then when you draw this circle, you get these two new points, D and E. And what you can do now is draw circles centered at D and E of the same size. I think that's what you're thinking, right? And then you get this new point F, where these two circles intersect. And then you draw a line connecting B and F, and that's a bisector. It takes this angle and splits it into two. Okay? So that's the kind of thing that the Greeks were interested in doing. It's kind of amazing to me that they thought of this problem at all, because it's like actually such an essential question, and how they thought of asking it is beyond me. But it's really cool that they did. And then ask questions like, okay, we can bisect an angle. How about we trisect an angle, split it into 3 equal parts? And this is a kind of similar story where for thousands of years, people were trying to do this. They thought it was possible. At some point, after a couple thousand years of effort, they got a little more pessimistic, and they realized, okay, maybe it's not possible. And it turns out it's not possible using a straight edge compass to split an angle to 3 equal parts. And the idea is to say why that's true, exactly go back to Galois. And it's exactly Galois' ideas about number systems that make this, that let you solve this kind of problem. Okay, so that's ancient mathematics. What about stuff that's a bit more modern? So maybe some of the older members of the audience might remember that in the 90s, it was front page news all around the world. Andrew Weil solved Fermat's last theorem. A big deal in number theory, used all the modern tools. You can find the name of the talk that Andrew Wiles gave, but it's modular forms, elliptic curves, and Galois representations. So Galois representations is exactly about these groups that we saw earlier and about studying them in a particular way, about representing them using matrices. And so you see that these ideas of Galois were essential to like some of the most cutting edge number theory that exists today. And that's still true today. Like there's areas of mathematics, for instance, there's one area called the Langlands program, which is extremely hot and active area of mathematics. It's a direct descendant of Galois' works. So that's in mathematics. And what about outside of mathematics? What about in our daily lives? So one thing, so I've been talking about these number systems. Like I was talking about the rational numbers and enlarging it by adding a square root of -3. The mathematicians have a technical name for number systems. They call them fields. And most number systems that we're familiar with, like the rational numbers or complex numbers, are infinite. But it turns out that there are also finite number systems, and those are called Galois fields. And Galois wasn't the first one to discover these, but it was his work that led to their like intense study and scrutiny, and that's why they're named in his honor. And I think this is an amazing example because Galois fields at the time of their discovery and in the first, I don't know how many decades of their study, they were kind of esoteric. They became over the decades a bit more prominent in mathematics. But the amazing thing now is that they're actually indispensable to modern life. We use them every day. All of us have here today in this room. So for example, here's a picture of the Voyager spacecraft. It's out there in interstellar space, millions and millions of miles away from our solar system. And it's sending signals back to Earth. And those signals, as they travel millions and millions of miles, they can get messed up. Certain things can happen. You know, zeros become ones, one becomes zeros. We need algorithms, we need code somehow that secures the message, that the message that we received from the Voyager is the message that was actually intended. And those are called Reed-Solomon codes. And they're absolutely just rooted in Galois fields. It's about arithmetic over finite fields. And every time you text a picture on a cell phone or a video or something, that's also using Reed-Solomon codes. So that's one way. Another way that we see these in our lives is in online banking. We want to secure our payments. There are like these cryptographic schemes that are used to make sure that the money isn't gone. And one very popular and very efficient form of cryptography is something called elliptic curve cryptography. This is again embedded in our technology all around us. And elliptic curve cryptography, again, is another example of something that's fundamentally rooted in arithmetic over Galois fields. Okay, so these are some interesting examples. Maybe on a less serious note, there's a game called Double or Spot It. Anybody here familiar with this game? Yeah. So the name of the game, you have these cards. These cards have these little cartoons on them. And every pair of cards has a unique image in common. Can anybody spot the image in common here? Danish? What is it? You might need a little help. Anybody else see it? So the zebra. You see the zebra? So these two, yeah. These two cards have a zebra in common. Okay? And so the name of the way the game is played is you have like, I don't know, 57 cards or something. You put 2 down, and every pair of cards has exactly 1 image in common. And you might ask, how do you design such a thing? So each of these cards has 8 different images on it. How do you design such a scheme so that the intersection, every pair of cards has exactly 1 image in common? Well, it turns out if you do things over Galois fields, it becomes very, very straightforward. Every one of these little images is a point in a space defined over a Galois field. Every one of these cards is a line in that space. And the essential point comes down to, well, 2 lines intersect in a point. So if you just set things up using these Galois fields, it tells you really where to put what on these cards. Okay. So I think this is, these are some important uses of these ideas in our lives. I think I mean, I think one thing that's interesting to note, maybe this is a good note to end on, is that, obviously Galois could have never dreamed of these applications 150 years after his life of his ideas. And I think it's interesting to think what ideas today are going to be indispensable to our life, 100 or 200 years from now. Somewhere somebody's working on them, and it's damn important. So I'll stop here. Thank you. And before you get going, Jordi, I want to thank you all for coming, but I also want to give very special thanks to SIMRI, Sydney Mathematical Research Institute, for organizing all this, specifically Larissa Fednik-Hoffman, who helped me a lot with the slides, Stefan Tillman, Executive Director of SIMRI, and Jordi, Director of SIMRI. Thank you, guys.
Thanks a lot, Oded. So thank you very much for this really beautiful talk. And we've got some good questions on Slido, actually very entertaining questions. So I'm not sure this is a real question, but someone says, why were there so many mathematicians dueling in ye olden days? And they would like us to have a duel as to who knows the most digits of pi, which I think we should do. But
I will not enter that duel, but if other people want to, sure. I know about 3 digits.
Okay, so I guess I win there. But on a serious note, in the slide giving the cubic, I also asked myself the same question here. Why ain't there no x squared?
Why is there no x squared?
Yeah.
That's a great question. The reason there's no x squared is because I just wanted to simplify the formula. It's more complicated if there's an x squared. And also, when I was talking about these Italian guys who were dueling, it turns out they only knew how to deal with these types of equations. The x squared was a bridge too far at that time. And then a few years later, they figured that out. So there's 2 reasons. Also, I mean, if you remember in the quadratic formula, there's a plus minus. There's more than one solution. For a cubic formula, you expect 3 different ones. And I didn't write down all the 3 different ones just to not make it too complicated. But they're also there. We also have formulas for those.
So there's a formula, but it's way more complicated.
Yeah. Yeah.
So there's 2 really good questions about. So you told us that when we have this quintic, you have a group, and somehow it's not solvable. Is it possible to say why it's not solvable or give some intuition there? It's a bit of a tough one, but
that's a tough
question.
One. So in this case of the quintic that we saw, so I said the Galois group has 120 different elements. To actually say what the group is not very hard. Imagine you have the numbers 1, 2, 3, 4, 5. And you look at what are called all permutations of these numbers, all possible ways of rearranging these numbers in any possible order. It's 120 different ways of doing that. That's what this group is. So you can get your hands on the group in very concretely. It's not some abstract thing. And then you study the structure of this group and you realize that it's in some sense very rigid about the type of subgroups it can have, the type of tower. So I mean, I don't know how technical I should get, but maybe that's a good way to answer that. We understand the group very well.
Yeah, maybe if you're one of the people that asked these 2 very good questions, you can talk to some of us afterwards.
Yeah, that's right.
It's fascinating, but not so easy to explain. Oh, we should have a question from the audience. Yeah. So if you don't want to use Slido, yep.
I had a question about, instead of just on the slide, he basically wrote this curiously written letter.
Yeah.
Right. Had he written any of this down prior? As in, would we have pieced it together without this letter, or is it thanks to that we have?
Yeah, that's a really great question. I mean, so I'm not a historian, but my understanding of the situation is that he did try to write it down earlier, and he sent it to really the most well-known mathematicians of the time, like Cauchy and people like that, and they couldn't understand it. It was way ahead of its time. And I think he wrote in a very complicated way. It was not the language that people were doing maths at the time. And I don't know if people would have known his solutions without the letter, but I do know that the letter has been indispensable over the intervening decades to actually understand what he did. So I think it was extremely helpful. I don't know if it was wouldn't have existed without it. I don't know.
One thing that's mind-blowing about that letter is there's a particular page of it, which is a summary of a 3rd-year class in Galois theorem. It's just boom, 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 all the statements that we spend a semester teaching, just on one page, totally mind-blowing.
Yeah. Question. If squared is only symmetrical to its 90 degrees, so in less than 90, say 89 degrees, they're all symmetrical. would you therefore refer to a circle as the infinitely symmetrical? Regardless of how much you turn it, it's always the same.
Absolutely. I would say that the square has continuous symmetry. You can do exactly what you said. No matter how much you rotate it, you get the circle back. So it's a, I think that's a good distinction of trying to understand, so I said we have this, we have these geometric figures. We could talk about their symmetries. And the idea of doing it in this kind of mathematical language is it really tells you the difference between them. So we both can all of us can look at a picture of a square and a circle and say, okay, they're both symmetric, but in different ways. How do we say that? Well, exactly what you just said is the essential difference. The circle has continuous symmetry and the square does not. I would say, sure. Yeah, why not?
So which Galois field does Doddle use?
F3.
F3, if that means something too. And so thank you all for these wonderful questions. Maybe we'll finish by a question that just came in, which is, what do you actually do, Oded, in terms of research?
Oh, thank you. So I work in an area called representation theory, as does Jordi, and I see several other people in the room here. This is an area that's very closely related to, Galois' ideas. It is a study of groups. So I mean, Galois invented these things, and we try to study them in different ways. We have these groups of symmetries, and we try to, in representation theory, we try to use matrices to understand the groups. We try to embed the group in something we understand better or have different tools to attack with, and this is linear algebra or matrices. And so what I do is try to study representations of groups, different ways of thinking about groups, either as matrices or sometimes in even more abstract ways, by just finding ways to try to get inside the group and understand exactly what its structure is like.
So thank you very much. Thank you all for coming.
Thank you.
And happy Friday.